Thank you. Thank you for the invitation, for the Antonio and SOC, and thank you for the impeccable organization from the LOC and the good food, and I like that. And this city is really nice, I must say. I mean, being by the water is really very nice. Walking in the evening, really enjoy. So you people working in here must say you're really lucky. Anyway, so today we'll talk about the host galaxies of fast radio burst. This work has been done mainly with people that are here listed: Luciano Nicastro, Elena Palazzi, Andrea Rossi, and Matteo Cinus, and my student at the University of Calabria, Claudia Gatti. Calabria is South Italy, so it's warm as here, so no problem for me. So today is the hottest day of the year in Marseille. Could it be? I don't know. There was worse. Anyway, so Kenzie yesterday presented already what the fast radio burst is, so I don't need to say much. Just that, so the intense radio emission or short duration, milliseconds duration, unclear origin, and the all cosmological distance outside of the Milky Way, but one case, which is inside the Milky Way. And what I want to say is that fast radio bursts are only detected in the radio. There is no other detection but in the galactic fast radio burst, which is seen also X-ray and gamma ray. So the most favorite origin is magnetar, which is a young pulsar in extreme magnetic field. And so there's still a puzzle. We still don't know what they actually are. So there are the possible origins for fast radio bursts. Some are expected not to repeat because they will merge into black holes and disappear, or things like this that you wouldn't see it again. All right, so statistics. Total number of fast radio bursts in last year was 800. Total number today is more than 5,000, thanks mainly to the contribution from the CHIME FRB collaboration. 123 are repeaters, for sure. There might be many more, just have to wait until to see them again. So it's a large minority, but they could be appearing again. And 2, maybe 3 are periodic, with very different period. And the one in the Milky Way is associated with a soft gamma ray repeater. And the soft gamma ray repeater is a magnetar that show X-ray and X-ray flares in a young pulsar. So here, this soft gamma ray repeater in Milky Way that is also a fast radio burst. You see it in the X-ray and in the radio. So about the host galaxies, what do we know? The first reported fast radio burst, the publication was in 2007, and is associated with the fast radio burst that was in 2001. I don't know why it took so long to publish this result. And the first localization at distance, it was because the host galaxy was seen. And so this is the radio observations, very large localization, but then they pinpoint a region that was a bright small object, was observed with Gemini, and they found the host galaxy, which is in this case is a small galaxy. So this was the first host detection. But so what do we do regularly? I don't do that, but I mean what people normally do. You have radio detection, and the localization could be really, really different. So you find the closest, most likely host. And this is an example of a recent paper. So you see the localization could be very different, very large, very small. If it's a nearby galaxy, even if the localization is large, you'd say, well, likely this is the host, but it's not always the case. Now, so we try to understand this population by studying the host. And the population right now is not super large, considering that fast radio bursts, there are 5,000 detections. Among these 5,000 detections, of course, some are repeaters, so they're coming from the same fast radio burst, but we know there are many. So I'll show you some very different cases, just to transmit the idea that this population is not spatial in any way. but they tend to be star forming or, you know, not super old. So for instance, this is a dwarf galaxy, the one I showed you a moment ago. And it's a periodic with a period of 157 days. Every 157 days or more or less it gets active again. It's a dwarf galaxy and low mass, kind of high star formation rate and low metallicity. So, which is something expected for a low redshift galaxy that is active. It's a repeater. This one was initially identified like an elliptical galaxy, so old and big, but just was an initial interpretation. It was seen again, and then they, with better resolution, spatial resolution, it was found to be a spiral galaxy, barred spiral galaxy, with some emission line there. Where's the pointer? Here, O2, the Lyman break, and this could be identified like a post-star burst, a massive galaxy that had a burst of star formation, and now is not very active, but it's a spiral galaxy. Then this is a one-off. This one was shown yesterday. I don't know if it was Alex or Kinsey. Maybe both. They showed that this is associated with a globular cluster. And that's a mystery because and this is a repeater, so if these transients are associated with magnetars, you wouldn't expect them to be in an old object. This is old, low metallicity, and not much dust. Repeater, and there are some that are like this. So it's very good localized. You see this in the R band and the K band, but there is no host detected to a very good limit here. So it's very deep. So where is the host? We don't know. But using the DM redshift relation, which is a way to estimate, so the dispersion measure gives a measurement of the electron column density. It gives an idea of the distance. If you consider the DM of this object is supposed to be distant, so maybe it's just a small galaxy that is just faint, you don't see it. Or because it's kind of bright, it could be a lower redshift. So this is a case where we don't know what it is. So a one-off. And finally, this one, which is associated with the persistent radio source. There are 4 of these cases that are known. We saw it yesterday from Alex and Kenzie. And these are embedded in a dense nebula, which is consistent with young magnetars. And again, this is a spiral galaxy, not super big, with solar metallicity. And what is interesting here is that the star formation rate you derive from the emission lines of the host is relatively low compared to what you get from the radio. So in the end, it is a mystery what actually are. So it's a repeater. But the numbers are increasing. So statistically, it's still too low to draw any conclusion. So we decided to build a database and eventually to make it public and to collect what is available from the literature. And to make it public and eventually open it to the community to contribute, because we expect numbers to increase very, very deeply, very, very fast. So we are working on the paper. It's in preparation, and the complications that it's taking time because there is so much stuff around, and for each single host galaxy there are multiple publications, and sometimes numbers don't agree and everything. So you can imagine it's complicated. But we expect to make it public soon, and we expect the community to contribute. Okay, so be patient a little more, and so you will get this available. So other database looks like this. It allows a web interface, interactive web interface. You can choose your catalog, your survey to cross-check your FRB, where it is and everything. And it's the most complete up-to-date, but still not public, unfortunately. But the numbers are very many. There are different catalogs here. The information about the FRB, everything that is available, about the host, about the available derived parameters for the host, the numbers that are published, But you can get these numbers and derive the host parameters yourself eventually when this will be public. So there are thousands of numbers here. So it is complicated, and one problem we have is to agree what we want to make public, what the columns we want to remove, because there are at the moment too many. All right, so today we have about 161 localized FRBs. The localization is also can be very different, as I showed you earlier. But they're distributed like this. You will say there's a cluster here, but no, I think it's just by chance, I imagine. Nature could be very nasty sometimes. But so the current status I showed you earlier about the host identification and distance. So at the moment we have 161 localized FRBs, 25 are repeaters. So the fraction is relatively large compared to the entire population because the repeaters they tend to be a little closer and the host galaxy is easier to identify. The hosts are identified for 156, so some of them don't have a host. 141 have spectroscopic redshift. 9 have photometric redshift, which is more uncertain. 11 have no redshift, and 5 have no identified host. So for a small fraction, we have the host, but we don't have information about the redshift. We think we have identified the host because the localization is an issue. So for instance, in this paper, 2025 from the CHIME FRB collaboration, you say, so this, the contour, the radio contour is about 20 arc seconds long and a few arc seconds across. And so you say, this is the FRB location in the middle here. There is a bright, kind of bright galaxy nearby. So they say, okay, this is the host. But then recently we saw with Euclid the same field. Euclid is much deeper, much better spatial resolution. And is that really the host? Or maybe is there something nearby? Oops. No, nearby, like somewhere, you know. So this is the FRB here in the middle. Could be something else, weaker. So, and you know, the distance from the FRB is about 10 arc seconds. So it could be anything. We don't really know. And there are many cases like this. Another one is this one. So the identification of the host is this one here. The FRB is there. But we recently, so it's 18.6 magnitude, it's a bright galaxy nearby. But we observed the field with LBT recently, and we saw that there are many more objects around. So which one is the host? Could it be that or this one nearby in the yellow circle? So in this identification of 150 something hosts, there is a large fraction, which might be a misidentification, okay? Now, today, so collecting results from the literature. How many minutes do I have? 10-ish? 11, wow. This is the redshift distribution for 150 plus 1. The one is the Milky Way galaxy. And these are the whole population. 24 are repeaters, which is 16%. And they tend to have lower redshift here because compared to this, to the total population, because the repeaters are easy to identify because they show up again. But statistically speaking, they don't show to be different so far. Maybe the number is still too small to identify that they're a different population. They could be different, we don't know. About the mass, 111 hosts have measured mass, and this is the distribution. Of course, they tend to be large. I mean, the last fraction is large mass because these are bigger galaxies, easier to measure and to observe. But there is so these are the repeaters, 21. And if you don't consider the globular cluster, which is much low mass, the two populations are not statistically different. If you include the globular cluster, then it's different. The story is different. But it's one object, and we don't really know. Now, we compare parameters for the hosts. For instance, this is star formation rate versus stellar mass. This publication is from 2022. It looks like there is a correlation which is expected for galaxies that are star forming. We did the same. We have more objects now, 2026. And this relation is this one here. It's consistent. So they go like normal star forming galaxies. There is a correlation between star formation rate and stellar mass, but there is a large dispersion, much bigger than what you would expect for normal field galaxies. Then we have the BPT diagram. BPT diagram is a diagram to identify objects that might be AGN, so with active nuclei for the host galaxies. And in this publication, you see that everywhere you can really draw conclusions whether FRBs prefer AGNs to normal galaxies or star-forming galaxies. We have a similar thing. We have more objects, and some look different. We have to understand why they're different, some of these objects. But again, the points are everywhere in this diagram, which is adding confusion to our understanding. And now the mass metallicity relation. The mass metallicity relation is a known relation in galaxies, star-forming galaxies. In the local universe, it's evolving with redshift. And this is something that Alex showed yesterday. I changed a little bit this diagram to make it more comparable to our diagram. So you see there is a relation. Yesterday, Alex said that these tend to be low metallicity objects, like they're, spatial galaxies in some way. And also she said that fast radio bursts, which are the stars, the repeaters that are the stars, tend to have low metallicity compared to the one-offs, hosts. We did the same, and for some reason it looks different. So I have to check this. I didn't have time to do it, I'm afraid. Because in our case, the red and the blue points that are repeaters and one-offs, they are not distinguishable one from the other. It looks that the relation is there, and that also metallicity tends to be high in some of these hosts. Because if I compare with field galaxies at comparable redshift 0.1, a 0.2 would be a little lower. They have high metallicity. So also this I need to understand, because the metallicity is another big issue, how it is measured. There are different methods and everything. We'll do this a better analysis on this point. Okay. Now, the last thing I wanted to say is that thanks to the DM redshift relation, it is possible to estimate the redshift of a large part of the FRBs, like you have seen many times. So if you do that, you can have a much larger sample, and then you can compare with other populations of other transients to see if they belong or they look similar to others. And this was done recently. So here in this diagram, you see a population of 439 one-offs FRBs. And the distance is estimated with the DM redshift relation. So you have a much larger coverage. And then you can compare to the cosmic star formation rate density, which has, this known shape, and long GRBs and short GRBs. So these are totally different objects. And long and short GRBs have different distribution with redshift. And it looks that FRBs are more similar to short GRBs than to long GRBs. So from this, can you draw any conclusion? Could be just by chance, but it's an information. Short GRBs are related to mergers of neutron stars or neutron star black hole binary systems. So they're very different from fast radio bursts, but for some reason they have a similar distribution. Of course, it's preliminary. the DM redshift relation is also very uncertain. You have to take care of the electron density in the Milky Way, a local electron density at the site of the FRB, and it could be very uncertain. All right, so conclusion. The number of localized FRB is increasing really fast. 156 are the localized FRBs, which is 96%, or so 156, 96.9% of localized FRBs have a host galaxy. If you don't have a host galaxy, identify, but 74% is the FRBs with the localization, which is within 4 arcsecond squared, which is those that are more reliable, all right? So some of the nearby FRBs, even if the localization is not super good, it's more secure because just on top of a galaxy or on top of a global cluster, for instance. So it doesn't matter if the localization is so good. But if you go far away, the localization is a problem. 141 have a spectroscopic redshift, and they are low redshift objects. We have the largest FRB database on host galaxies. We want to make it public very soon, and we want your contribution to make it larger and more interesting. Many of these host galaxies are spiral galaxies, many dwarfs, star forming. Old galaxies are not common. And to what we have seen, there is no significant difference between hosts in repeaters or one-offs. But as Alex showed yesterday, we still don't know enough because the statistics is still too limited. And we found the mass metallicity relation in these objects. And thank you very much.
Thank you, and thank you also for staying perfectly on time, which means we have time for questions.
Yes.
Good morning. Thank you for a nice talk. I have 2 questions. One is, when you search for the host galaxy, is it somehow biased in that you're looking for something that is in DM similar to the redshift of the host?
Well, we don't identify.
Or it's completely like independent?
We don't identify galaxies. We just take what is available in the literature. But of course, everybody's doing things in different ways. Mm-hmm. And of course, that makes things more complicated. So it's not homogeneously. Some of the things like the metallicity, we derived this, we had that under control. But the identification of the host, we don't do it, generally speaking. We did some because, for this object I show you with the radio percent of the radio source, we didn't do the identification, but we studied the host. But we rely on what's available in the literature. We have to, because otherwise we'll be very limited.
And the second, very short, like the catalog is from all the telescopes, like the radio telescope, FAST, CHIME,
yes, anything that is available.
Okay.
We don't discriminate in that regard.
Question over there.
Can you comment on the last figure that you showed with the comparison with the cosmic star formation history, whether it was corrected in some way for, I don't know, the fraction that's expected to be missed as a function of redshift, or is it just plotting counts?
Say again. Sorry.
The redshift trend, is there any correction for the fact that we're probably missing a decent fraction as we look at high redshift events, or is it just comparing counts at this point?
I don't know.
Okay, thank you. I'll check out the paper.
But yeah, I mean, I think they must be corrected because I think short and long GRBs there must be. I don't know. Good question. Yes. Thank you.
Question over there. Yeah.
I assumed it's correct because also the cosmic star formation rate density is correct for this. But I mean, the correction is so arbitrary that we don't know. Yes.
Hey, thank you for the really nice talk.
Thank you very much.
Can you go back to the metallicity slide? I have a question and also a clarification. This one's my bad, but I think your results are actually really consistent with this because the colored stars don't represent repeaters, but they just represent ones with PRSs. but there's some repeater stars in green at the top. So
Oh,
it looks
okay.
consistent to what you're seeing.
All
So
right.
I think
You're
you
fine.
don't have to stress. Yeah. We're
Too bad.
consistent, which is
Okay.
good. And then the second question is, do you know off by probably not, but the one-off that has low metallicity on the right, do you
Yeah.
remember what FRB that is?
No.
Okay, that's fair. I will find you because I'm interested in it.
Yes. Sorry.
Okay, so it looks
So-
like there's one question online.
Yes, we
Yeah.
have one.
And that will be the final question because we need to switch to the next speaker. So please go ahead. I don't know. Can you unmute?
Yes.
Or how does this work?
Hello, Sandra, nice to hear you. I have a question about selection effects because
Hi.
to get the exact position, you need interferometric data. What is the fraction of fast radio bursts which have accurate enough position out of these 5,000 or so? Because CHIME data are not good enough to have a localization.
I don't know. The CHIME population is 3,500. And how good it is, I really don't know. Maybe Kenzie can say this. Is she here? So the localization, I don't know. I cannot answer this. I mean, normally the interferometer, those that identify with the interferometer look good localization, but not always. I mean, this very long, narrow contour, these are interferometric data, but it depends how many antennas you use, you know. So it's a problem.
Thank you.
Who is the speaker online?
Oh, sorry.
Who is the speaker? Okay, thank you, Misha.
Okay, well, let's thank Sandra again. Yeah. So we are going to continue in the theme of fast radio burst host galaxies, now from by Ashley Chrimes.
Great, thank you. All right, yeah, so good morning, everyone. I'm Ashley, I'm a research fellow at the European Space Agency, and to continue on the FRB host theme, I'll be talking about FRB hosts with Euclid DR1. Okay, so I'll go through this pretty quickly since we've had quite a few talks on FRBs at this point. So yeah, the nature of FRBs remains unclear. They're likely from sort of some compact objects, maybe a magnetosphere, and a magnetar connection is suspected, not least because you have this sort of almost continuum from the galactic magnetar FRBs up through the one outside M81, which we'll talk about later, and then the cosmological one. And so the motivation for doing this, partly it's to study the host populations, to see if that gives you some clues about the progenitors. This is, of course, complicated by the fact that we see some FRBs in ancient stellar populations, including globular cluster and some massive ancient elliptical galaxies. And is this telling us that maybe there's alternative ways to produce magnetars, or maybe it's telling us that not all FRBs are coming from magnetars? Another reason to look at the hosts and to get the right host association is for the various cosmological purposes that we've heard about already at this meeting. And so Euclid is a great way to do this. So it's mainly a cosmological mission, but it's doing a wide survey of eventually a third of the sky, but in the first data release, it's covering 2,000 square degrees of deep high resolution imaging. It's reaching, I think, 26 mag in VIS and 24.5 in the infrared bands. And the first data release is now split into two phases. The first half will be in November 2026, and then the second half in mid-2027. And so the FRB host project is just one of many in the supernovae and transients work in Euclid. Okay, so our FRB sample is the host sample that Sandra just spoke about. So it's 161 FRBs that are well localized, typically sort of arc-second, a few arc-second level, and they're from various different surveys, DSA, ASCAP, NIRTRAP, etc., and others. And so 23 of this 161 are within the Euclid DR1 wide survey footprint. We can also potentially consider the CHIME ones, but they tend to have larger positional uncertainties, although there are better positions from CHIME to come, which we'll see later in Sandra's talk. And yeah, this is just the distribution of where the FRBs in our sample are, and they just sit in the obviously the wide field survey footprint. Okay, so to do the host galaxy cross-matching, we have two different methods. So I should say that we first query the Euclid deep fields. There are none of these FLB hosts in the deep fields. They're all in the wide survey. But the two ways that we identify a host galaxy, the first one is the directional light radius, or the scaled directional light radius, I should say. And this is essentially like a host normalized offset, but it takes into account the ellipticity of the galaxy. And so your half-light radius varies as a function of angle around the galaxy. And you choose the host which minimizes this scaled DLR. There are some biases there. This obviously chooses galaxies for which you're biasing against galaxies that have a large offset. And then there's also the p-chance, which we're very familiar with in this room. And so this is taking into account the distance from the galaxy, its magnitude, and what the chance of just being there in projection on the sky by chance is. And so that has been adapted to take into account again the ellipticity of the FLB error ellipses. And there's a potential bias there towards brighter and on average lower redshift host galaxies. And all this work is being done through ESA's data labs, which is a great way to, rather than downloading loads of data locally, taking your scripts and running them where the data is. Okay, so the cross-matching results, and this is all very preliminary, I should say. So out of our 23, we have 20 that have at least one catalogued host candidate. And in all but one of these cases, which has Hubble imaging, Euclid is providing the best, i.e. the deepest and the highest resolution imaging available. And this is just a subset of 6 that I'm showing here. I should say Euclid has 4 bands. It has the visible band, is sort of similar to an I band, and then it has the infrared YJH. And this is just some more examples. This is showing the improvement in spatial resolution that you get versus the previously published data for these hosts. You can see that it's really quite a big jump in spatial resolution and depth. Okay, so I'm going to speak briefly about a few interesting cases in this sample. So the first one is this one, the globular cluster FRB, which happened to be in the footprint, which is quite nice. We can actually resolve the globular cluster. You can see the stars around the outside of the cluster there. Now, the interesting thing here is that if you put this much further away, at a cosmological distance, then you wouldn't have seen this globular cluster. And so there's a question, which I think Sandra hinted at in the last talk, as to whether you should consider, when you're comparing to the rest of the sample, whether you should consider the globular cluster as the host, or whether you should consider M81 as the host, which is the galaxy outside which this globular cluster is found. Another one is 2023-0808F. So this is the only case in the whole sample where the DLR and the p-chance host selection criteria actually select different host galaxies. And it's essentially because with the DLR, this is lying right on the end of the disk. So you can imagine sort of the host normalized offset in this direction is quite low, but this galaxy is actually brighter. And so these two selection criteria differ. But actually in this case, they're a common redshift. So there's no implications for the cosmological sort of applications here. Yeah, another one I want to mention is this one, 2023-1010A. And so, again, credit to Sandra for this figure, but when you look at the position of the FRB, which is sort of at the end of this disk here, in the Viz band, you can see sort of a blob of bright emission, coincident with where the FRB is. This is actually a change in the host galaxy with respect to the literature. It was previously assigned to this blue object here, but we now think it's actually this galaxy. And yes, we want to investigate what this is, whether it could be related to the FRB. I'm going to do some SED fitting at that position. I'll come on to the SED fitting in a second as well. I think the last specific one I want to talk about is 2023-1210F. So this is interesting because there's a galaxy underlying the FRB position, which is only detected in the infrared bands. So this was previously thought to be the host, this one that's visible in Viz with a large offset. But yeah, in the YJH, you can see this galaxy underneath this faint emission. Now, there has been some previous SED fitting for these two galaxies, providing photometric redshifts. And the dispersion measure in the Maccary relation favors G1 as the host. But we're going to, again, do some SED fitting and see if we can improve these constraints with the Euclid filters and see what we find there. And then, of course, we can do sample statistics. So, for example, we can look at the offsets, the offset distribution. Now, the slight problem here is that with these localizations of level sort of arc seconds, you tend to bias away from, you tend to bias towards higher offsets. And actually, this follows a Ricean distribution, these offsets. And when you have a large positional uncertainty with respect to the offset from the host galaxy, so it scatters the FRBs to higher offsets. And so really to get around this problem, we need to get, we need to reduce the positional uncertainties by a factor of quite a few to drive down these uncertainties. And that we'll hear talks about that later in this session. Again, you can do, yeah, this is another example of the same kind of thing. So you can also measure, for example, fractional flux. So the fraction of the light underneath the position with respect to the total in the galaxy. And again, because these are quite large positional uncertainties with respect to the host galaxy size and respect to the offsets, this is quite problematic, and it pushes us towards larger, or to say lower fractional flux values in this case, i.e. we get sort of scattered towards lower pixel values around the host. Yeah, so this is the M81 case that I come back to. So the globular cluster is down here somewhere, and if you put this at a cosmological distance like the rest of the sample, then of course you wouldn't be able to detect that globular cluster in the first place, and you would instead just measure this as being at a relatively larger offset from the host. So you can see this in the host absolute magnitude distribution. That one really stands out clearly. Yeah, and so there's an interesting question here. Also, if you invert this, are some of the FRBs which are at high offsets from the hosts at higher distances, potentially in the halos of their galaxies, and potentially also in globular clusters? Yeah, so we're going to do SED fitting for all the hosts in the sample. We're going to try and do where the FRBs are localized well enough, SED fitting at that position. But you can see this is so preliminary that there aren't actually any fits to these SEDs yet, so I'm going to move on. And yes, so doing the precise locations within the host galaxies is, of course, the ultimate aim. So this is with number 4, for example, with 2018-09-16b, where you measure this offset from a star-forming region within the host. And so there's one FRB in this sample which is quite well localized, significantly less than an arcsecond, this one. And so you can sort of say, okay, how far is it from the nearest blob of star formation in that galaxy? In this case, it's about 1 kiloparsec. Of course, there could be some more star formation underlying that position. But to demonstrate the point, if it is 1.3 kiloparsec from that nearest spiral arm, from that nearest blob of star formation, yes, you can then play a game where you ask, okay, for the typical ages and velocities of various different potential progenitors, which of these look plausible? And so, for example, a magnetar scenario here might be quite difficult because you need a very high velocity to go that far within that age. Although, as a caveat to that, magnetar ages might actually be underestimated, as we recently showed in another paper. But that's a different talk, so if you're interested in that, come and talk to me later. And yeah, this will be possible in the future with CHIME, Outriggers, Chord, and the SKA, etc. Okay, and to summarize, Euclid is providing the best data for most, well, many FRB hosts, building on various host studies in the past. Overall, the hosts seem broadly similar to core collapsed supernovae hosts, but they might be more offset, the FRBs, from star formation within those hosts. But we need to drive down the positional uncertainties on their positions to verify this. In progress is the SED fitting, putting limits on underlying globular clusters in the cases where they're near enough. And I should also say that this is not the only host project going on within Euclid. There's also papers on GOBs by Ben Schneider, also supernovae and type 1a supernovae ongoing as well. And I've been asked to advertise the ESA Research Fellowship. So if you're at this career stage and you're eligible and you're interested, please give it some consideration because it'd be great to have more transient science representation at ESA. So I'll stop there, take any questions, thanks.
Questions for Ashley? Sandra? No.
Thank you. So the global cluster FRB, do you think this FRB, is this in the global cluster or not? What is your opinion?
Do I think it's in the global cluster? Yes.
Could it
Do I
be
know
that
what it
there's
is? No.
just by chance, it's just there because, you know, Euclid is going to resolve this? Can it be that there is something fainter, more distant?
I think the position is so in the center of the cluster that I think the
But
chances of
I
being
see Euclid wonderful global cluster images where you see galaxies and behind, very beautiful, many galaxies behind.
Yeah, sure. No, but this one, I think there's nothing else around it, and it's very much in the center of that cluster. So I think it's fairly definitive.
So while people think I have a question, so this is not at all my field, but I was kind of stricken by both in the first talk and in this talk. We saw some plots where like FRBs perfectly tracks the short GRB population. Not at all. So do you think there's a chance we're just blinded by this idea, oh, they must be massive stars, they must be magnetars, and there's actually they're old population and we're just very like attached to this magnetar?
I wonder. I mean, some of these are at quite high offsets.
Yeah.
I mean, even with the large uncertainties, you can see they're at relatively high offsets. So who knows?
Yeah.
Yes, I don't think we know yet.
Sorry, very quickly. It's what are the magnitude limits of the Euclid data you have?
At the magnitude limit.
Yeah.
Yeah. So it's, I think in the wide survey, it's down to 26 in vis and 24.5 in the infrared.
Okay. Yeah, not bad. Because I think that there is a message that you deliver very well, you as well the talk yesterday by Ben Stappers is that, and I think it's true also for short gamma ray burst, that if you don't have data that are very deep, these offsets are okay. In some cases, for sure, they are not. They may be not correct.
Yeah.
And yes, and to have at least Euclid is already a good thing to go to the 26. But we saw also in Gerbios and as the example of yesterday that in fact HST or GWST are the answers, but already to go to the 26 in a homogeneous way, this is very nice for this kind of studies.
We have time for one final question. If there's none in the audience, I'm going to use chair's privilege again, actually, because I was also curious for this. I mean, host localizations is hard, and I'm wondering when people are doing this, can you use the DM information as kind of a prior on what's the, if you have like like I understand that's problematic if you want to do cosmology, but if you don't want to do cosmology, you just want to know like which galaxy is more likely. Is that something people are doing, or?
Yeah, I think that's entirely possible. It's a question of which way round you want to do it.
Yeah.
But yeah, I think in some of these cases where there's multiple candidates, that might be a possible way to distinguish between them. Yeah.
Okay, we should move on. Let's thank the speaker again. And our next speaker is Martyna Chruslinska. I'm sorry if I butchered that. Who will give us a piece of warning, I think, about metallicity and transients. Very nice. Yeah. See, I should have seen that. Sorry.
All right.
Yeah.
Thank you.
I'll give you 2 minutes.
Thank you. Hello, everyone. So my name is Martyna Chruslinska, and I'm a fellow at the European Southern Observatory. And indeed, you're going to get a bit of a break from FRBs for this talk. In fact, I would like to invite you to think about how the things I'm going to discuss apply to your for your mental health. I'm going to try and avoid this. So I'm inviting you to think about how this applies to your favorite transient. Okay, so we often find that there's some metallicity dependence in the formation of transients, especially those linked to massive stars. And this may come from the models. You can see a somewhat arbitrary selection from the models here, spanning per instability supernovae, black hole mergers. So these are gravitational wave transients, as I like to think about this, long gamma ray bursts. And you probably cannot read those figures. Don't worry. I just want to highlight the overall dependence. So every figure shows some measure of the formation efficiency versus some measure of metallicity. And there'll be more examples. And you can see that overall this drops towards high metallicity. And sometimes this is very sharp, right? So there's almost like a threshold in metallicity above which some of the processes that lead to formation of those transients are becoming efficient. So this metallicity preference has implications, as we've already heard, for the expected host galaxy properties, as well as the redshift evolution of rates and population properties of those transients, which is something that we can test observationally. Right, so this is nice, but we can also just start from observations and try to deduce whether some transients have a preferred metallicity range for their formation. So actually the star of my talk is going to be this central part, because to do this exercise we need to have a fairly good idea of what is typical for all the stars or all the galaxies in the cosmic volume, so that we can do this comparison and see that the transient select some special host galaxies in some way, or if there's, that the rate evolution does not simply trace the overall cosmic star formation history. So the minimum is to see that there is a difference. And if we actually want to deduce what's the metallicity dependence, then we need to be, more quantitative, and we need to be able to quantify something like a star formation rate weighted birth metallicity of stars over cosmic time and as a function of galaxy properties. And the curve in the title of my talk refers to the fact that, to kind of close this loop and feed the observations to models, we also need to be a bit careful about what we mean by metallicity in both contexts. So especially that, all the examples I showed you refer to massive stars. Well, we know that massive star progenitors of transients, massive stars are sensitive to metallicity in their evolution. And probably the primary reason for that is the metallicity dependence of the stellar wind mass loss. So, more metal-poor stars have weaker winds, which means that they can retain more mass and angular momentum as they evolve. And this can have secondary effects. So there may be more differences in how such stars live, die, and how they interact if they are in binaries, depending on their formation metallicity. And actually, what is important is that not all metals are equally important in this context, right? So iron group elements dominate the opacity and the driving of radiation-driven winds of hot stars. So often when we say metallicity in the context of stellar evolution, we actually mean iron abundance. And so keep this in mind, because now I want to think about which metals are actually used to determine metallicity in star-forming environments. And if you're not working in this, well, let me tell you that it's almost never iron, and it's almost always oxygen, right? And this is not very surprising, because oxygen is the most abundant metal. It has strong emission lines that we can now see up to very high redshift with JWST, so that we can use it to map this evolution of the oxygen abundance as a function of galaxy properties. So you can see a recent example of the mass metallicity relation mapped between redshift 0 and almost 10. In this case, there's a stellar mass on the horizontal axis, and also as a function of cosmic time, as you already see in this figure. So there is a bit of a mismatch between what we can derive for representative samples of star-forming galaxies as a measure of metallicity and what we actually need. And the easiest scaling, the easiest scaling that you can think of to go from, okay, this is the oxygen abundance that I have, and this is the iron abundance that I need, which is assuming there is a solar abundance pattern, well, it's usually not correct, because, we know that these two elements are produced on different timescales. They have different nucleosynthetic origin. So oxygen is abundantly produced by prompt sources, core collapse supernovae that happen shortly after the star formation, while iron is also abundantly produced by type 1a supernovae, and those happen with a wide range of delays. So this iron enrichment is lagging behind, and it's actually pretty, special time when we get this solar abundance ratios. However, we proposed a method to go around this, and this method has a form of the scaling relation that you can see here, which allows us to kind of guesstimate what's the iron abundance of a star-forming galaxy if we know its oxygen abundance and specific star formation rate. And the specific star formation rate, which is the ratio of star formation rate over galaxy star mass that you see on the horizontal axis here, is essentially used as a proxy for time. So it allows us to deduce whether the current chemical enrichment of a galaxy is dominated by prompt sources. So it would have elevated oxygen to iron ratio, relative to solar, or whether there's been already significant enrichment by these delayed sources that have enhanced iron production. So it would be, it would have lower oxygen to iron ratio on average. And we can combine this with what we know about the statistical properties of star-forming galaxies in the cosmic volume to quantify this thing, the star formation rate weighted birth iron abundance as a function of cosmic time and galaxy properties. So broadly speaking, we combine information like, the fact that low mass galaxies are on average more common in the cosmic volume, but they have lower star formation rates. And we further use the information that the oxygen and iron abundances correlate with stellar masses and star formation rates of galaxies. And then we can use that to map this iron abundance versus redshift plane. So here now is on the left, early universe is on the right-hand side of this plot. And this is colored by star formation rate density. So you can see that most of the stellar mass forms in the yellowish part of this figure. And you can see that the iron abundance increases towards present day, but there's always a broad distribution. And just a note here that this exact result is sensitive to uncertainties in those galaxy population properties. For instance, how many low mass galaxies actually are there at high redshift. So we discussed this in the paper, and we propagate this to the final results, so you can see how this depends on various uncertainties. We are also sharing the results via GitHub and all those, so you can use them. We also compare oxygen and iron-based results, and I just want to highlight here this offset between the star formation rate weighted average abundance in terms of oxygen and iron metallicity. So you can see there's an offset that increases with redshift, basically reflecting this delay in iron production relative to oxygen. And now I'm going to ask, what is that to our question about the transients of massive star origin. So I'm just showing you this oxygen-based and iron-based distribution next to each other. You can see there are obvious differences. And this means, for instance, if you think about the transient that has some metallicity sensitivity in its formation, if you were to use oxygen for metallicity, you would infer, for instance, a different rate, so how common or how rare this transient is, and different peak formation epoch than if you were to use iron. And in particular, if you think about transients that have some possibly strong metallicity formation threshold, then they are particularly sensitive to this low metallicity tail of the distribution, which is where these two are the most different. So there's always, in a way, more low metallicity star formation in terms of iron, and it extends to low redshift when you compare this to solar abundances. I'll move towards host galaxies for the last part of my talk. So I'm just going to give you two very simplified examples. The first one, I'm going to start from a model. So I'll use this pulsational per instability case shown in the figure in red, just because it's very conveniently, its formation efficiency can be approximated pretty much by a step function with a 1/3 metallicity threshold. And now, depending on how I understand metallicity, I would infer a bit different host galaxy mass distribution at redshift 0. So you can see that overall, the preference is to lower mass galaxies compared to the overall galaxy population at the redshift. But if I were to use oxygen, then the selection is a bit more extreme. So the preference is for lower mass galaxies than if I were to use iron-based metallicity for that. And for my second example, I'm actually going to start from the observed mass distribution. So I look at superluminous, hydrogen-poor superluminous supernovae hosts. And this is just comparing this as a cumulative distribution with respect to the overall galaxy population, just star formation rate weighted at the median redshift of the sample. And you can see that there is this clear offset. So this is usually understood as the fact that there's some metallicity preference in the formation of those transients. So we need lower metallicity hosts, and I can fairly well match this mass distribution by just looking at the oxygen base, so mass metallicity relation with the population scatter, and I would infer something like a 1/3 solar metallicity formation threshold for those transients. However, this is likely not what I want to feed into my star models to scale wind mass loss rates and describe the evolution that leads to the formation of those transients. And in fact, you can see that I can equally well match this mass distribution, assuming that there is a formation threshold in terms of iron abundance. And this would give me something like a 15% solar iron abundance threshold. So compared to relative solar abundances, this is like twice lower than what you deduce using oxygen abundances for this. Yes, so you may want to keep this difference between oxygen and iron abundances in mind. These two elements in particular are produced on different timescales. So this matters for the interpretation of transient population properties and predictions, especially when we use host galaxies or redshift evolution to deduce what's the origin of the transient. Thank you very much.
Thank you. That is super interesting. Any questions? I think Win first.
Thank you for a very nice talk. So in terms of using iron, do you have any thoughts or comments on using, say, supernovae spectra in the ultraviolet, which have a lot more iron transitions, and if we were able to access Lyman alpha as well to like anchor the hydrogen abundance of metallicity? So this would be a local environment probe, not global. But this probably comes with many degeneracies, and I was just curious, like, what you think about that.
Yeah, so I don't know if you're like asking this in a specific context. Just so I see this as something that can be useful to, for instance, test the approach that I propose. So it is oxygen over iron specific star formation rate relation. If we know for sure that core collapse supernovae don't have any metallicity bias and they just follow star formation, and we can deduce iron abundances from their spectra, and on top of that we have information about their host galaxy properties, we can start testing this and narrowing this down. So yeah, I think any probe of actual iron abundance in star forming environments is very useful, because it's very difficult to do this with standard methods, and it's almost impossible to do this in the same way as we derive oxygen abundances in star forming environments. So in that sense, I think this is super useful. I think it needs to be like tested and calibrated, because as far as I'm aware, it was not really applied in this context too much, right?
Thanks a lot. I think it's very important what you pointed out. And in a paper we did in 2019 by Palmerio et al., when we studied the metallicity threshold for long gamma ray burst, in fact, to reconcile what we saw from the observation and the models, this difference between oxygen metallicity and iron-based metallicity is really something that we really pointed out as a reason for the discrepancies. But I was wondering if you are working also on prediction, invoking also difference in the IMF, because this is another very important factor, especially when you are dealing with massive stars. So I was wondering if you have some work ongoing on this and some results.
Yeah, well, I mean, IMF is always difficult because it affects so many things, right? So, and there are many ways I could try to answer your question, but yeah. So for the approach that I'm proposing, I think this is kind of IMF safe. Like we did, nothing comes from, for instance, in terms of this oxygen over iron specific star formation rate relation. We calibrate to observations where possible to avoid, for instance, this ambiguity from the models that everything would be shifted around if you assume a different IMF. So in that sense, it's down to interpretation if you want to infer IMF variation from such differences. Yeah, I mean, I can probably spend way too much time discussing this aspect.
We can discuss later.
It's within my interest, and I did some work. It's not immediately related to the specific topic I discussed today, but I'm happy to follow up on this during the coffee break.
Okay, we should move on to the next talk. So let's thank the speaker again. And we have one more presentation before the flash talks. Moving back to FRBs again, Sandra Ross, I think will tell us how to localize them better.
Hi everyone, I'm Sandra and I'm a PhD candidate here at Marseille. and I work on local environments of fast radio bursts with CHIME and Euclid. Kenzie gave an amazing overview yesterday on fast radio bursts, but as a quick refresher, that it's extragalactic radio transients. They're brief, luminous, and even though we've been studying them for almost 20 years, we still don't fully understand their origin. As was stated today, they come from various environments, from star-forming regions to quiescent regions, and that imposes a question on the progenitor models. Is it one model that can describe different environments, or do we have multiple progenitor models? So that's why it's important to study the host galaxies and specifically the local environment to constrain these models to the best ability. We observe radio transients with radio telescopes. I work with CHIME, Canadian Hydrogen Intensity Mapping Experiment. It's located in British Columbia, Canada, right here. And recently it has been upgraded with 3 more stations, which we call Outriggers, on different baselines. And these different baselines allow us to triangulate the location of an FRB to a very high precision. With 3 Outriggers, we're achieving sub-arc second localization precision. And with CHIME field of view and Outriggers, we also achieve about 1,000 FRB samples per year. So our numbers, as was stated today before, are growing very rapidly. So we've been bringing Outriggers one by one online, and we've been publishing Outrigger catalogs also one by one. So the first one was published in 2024, and it included the localizations only for 1 Outrigger. So the closest one to CHIME, so the localization precision was the poorest, but we are soon publishing the Outrigger catalog 2 that includes localizations from 2 Outriggers, so the closest one and the furthest one. And the long baselines give us better precision. And this sample would be almost twice as big and will be published soon. And right now we're running already 3 Outriggers. So in the future, we'll also compose OutCat 3, where all 3 Outriggers will be working and we'll have the highest precision available at the moment. And just give you an example, I think this example was already shown before, but this is the localization precision with 2 Outriggers. Even though it's already great, it's already on a tens of arc second scale. And you can see the 1 sigma localization uncertainty would be the solid ellipse, and 3 sigma localization uncertainty is the dashed ellipse, even though again, it's great. But we see that even in 1 sigma, we see multiple objects, and even though probabilistic host would be this galaxy right here, we're not certain on that, right? But with 3 Outriggers, we are achieving exciting results. So this is an example of a study with JWST as a follow-up. So on the upper tile, you see the host galaxy and the localization of FRB 2025-0316A. And at the bottom, you see a really zoomed-in version of the same field. And it shows how high precision in localization can show us what is happening not just with the host galaxy as a whole, but in the local environment. So here you see how they say 5 near-infrared sources coincide with 3 sigma localization error, and specifically 1 coincides with 1 sigma localization error. But it's still challenging to associate every localized FRB with a host, especially if hosts are faint or distant, and we know they come from faint galaxies. For example, in this study, they show that the FRB was associated with low luminosity dwarf galaxy. And as an example, GTC, the telescope in the Canary Islands, was able to resolve a dwarf galaxy right here. But on the right side, you see MMT in Arizona that unfortunately didn't resolve anything in that region. And that highlights the challenge that sometimes we need deeper surveys to see where FRBs are coming from. And that's why we want to incorporate Euclid. Euclid allows us to have deep, high-resolution optical and near-infrared imaging that will enable that detection of faint and distant hosts. And also we can characterize the local environment of those hosts that are a little closer to us. This is the map of Euclid footprint with OutCat 2. And the footprint is what we expect to be by 2030. So what we have at the moment are yellow FRBs and orange ones. which is not the big sample, but as Euclid going to continue surveying, we're also going to have more and more localized FRBs moving forward, so the sample is only going to grow. But meanwhile, what we could also use is the unions, which is the array of 3 telescopes, ground-based telescopes that give us the deep photometric survey. And there's a couple advantages to use unions. First, we have more sky coverage available right now. You can see that what unions cover right now is in blue area, and what Euclid is supposed to cover by 2030 is surrounded by the yellow border. And another useful thing we could use with unions is the fact that they cover 2 bluer bands that aren't covered by Euclid, and that would be specifically useful with star-forming regions. But let's get back to Euclid. I just want to show how amazing the improvement is with this device. On the left side, you can see what we had with the SE Legacy survey. And again, the solid ellipse shows the 1 sigma localization uncertainty, and the dashed one shows 3 sigma localization uncertainty. This dot shows the most probable host that we identify with a software called PATH, which identifies the host using probabilistic methods. And on the right side, you can see the reproduction of the same field, the same FRB, and even at the first glance, I think the resolution difference is impressive. But the real advantage is we can actually zoom in on arcsecond scale with Euclid, and look what we see. The previous host, the most probable host, was around 3 sigmas away from our localization. And what Euclid shows that it resolves a new near-infrared object that coincides with the position of FRB to 1 sigma localization uncertainty, which is exciting because that shows again how much Euclid can uncover in the future in FRB science. And as I said before, it's important to look into hosts and their environments, but since the sample is growing really fast, we cannot do it by hand anymore, and we need that to be automated. So we have a pipeline in CHIME that is called HostCat. So it starts with host identification with PATH, the software I just mentioned. And then it can do a few things. So it can take the photometric surveys available in public and perform an SED fitting with Segal to extract stellar mass. It could perform spectroscopy to extract spec-Z and constrain SED fit. Or we can also measure the spectral line fluxes to extract star formation rate and metallicity. And last but not the least, we can also extract morphology, inclination, and size with GalFit. And this is my responsibility in that pipeline. This is what I've been working on. And this branch is already being tested. And as soon as it passes the tests, we will extend it to GalFit M, where M stands for multiband. So we will be able to jointly fit the near-infrared filters with visible images to extract photometry, and that will allow us to bypass the public surveys, which is going to be particularly useful when we study not just the host galaxy as a whole, but the local environment, so we can extract the photometric properties of the local environment. So the next steps, we will implement GalFit in our pipeline to see if there's any preference in the galaxy type and the offset from the Galactic Center for FRBs. We also want to continue to study local environments with Euclid, extract the optical properties like star formation rate, stellar mass, metallicity, correlate these parameters with FRB properties, for example, the Faraday rotation measure. We want to incorporate Euclid, especially while we're still waiting the survey of Euclid to be done and published. And as a long-term goal, we're running 3 outriggers, so we will compose and issue OutCat 3 with the promised millisecond localizations in the future. Thank you for your attention.
Thank you so much. We have time for a few questions, but I also want to ask maybe during the Q&A if all of the Flash Talk presenters can sort of slowly make their way down as well. Questions for Sandra? So I'm actually, well, people think, I'm very intrigued by these, that you're actually able to do these local environments. But I'm curious, with just Euclid photometry, what kind of things can you actually say? Like, what kind of SED fits will that?
What kind of what, sorry?
Like, I'm not so, like, with just the Euclid photometry, can you really say very much, like characterize the environments, or do you then also need to go back to public surveys to get more data, basically?
We hope to do that with our pipeline, just our pipeline, because we want it to be separate from surveys. When we want to look in the local environment, this data is not available for a specific region in the galaxy usually. But we also will test and see what's best. Maybe sometimes we can use the public surveys to calibrate or make sure that our pipeline works well. Yeah.
Over there, yeah.
Hi, thanks for the very nice talk. I was just wondering what do you know so far about the galaxy that's next to the bright galaxy, or are you allowed to tell us what you know already about it? I mean, is it at a similar redshift, or?
So we don't have a spec Z for these galaxies, but as far as I know, the photo Z's are different. So the big galaxy has around 0.3 photo Z, and the small blob has 1.2. So they're quite apart according to photo Z, but we are not sure yet. So once the pipeline is done, we're planning to run that as a first thing and see what we can extract.
Yeah. Oh, yeah, sure. Daniel.
Just starting from also that specific example that you showed, when you have already a galaxy which is likely to be associated, but then you go deeper and you find a new galaxy, of course, you always have these, like if they are both associated, maybe it also indicates that the galaxy is maybe a joint system, and that would tell something about the physics. If you are always in satellite size of massive galaxies, that would be itself an interesting point. Just this comment.
Yeah, when we first saw this, we thought it's a satellite galaxy, the first thing we thought about. But photo Z says it's not, but we're not sure. So this is something to follow up on.
I mean, I was also really struck by this example, and I was wondering, I mean, it's on the one hand, it's wonderful that Euclid is so deep, and you're probably going to find many of these where you turn around, but then what are the hopes of getting spectra of, like, actual spec-Zs of?
To be honest, I'm not so sure, because we have the majority of FRB population below redshift of 0.5, and Euclid optimized between 0.9 and 1.8 redshift. So there I'm not entirely sure, but we'll see what we can do with Euclid. And if not, maybe we can use different surveys to complement our study.
Okay, if there's no more questions, let's thank Sandra again. And the final thing before the coffee break is we have a series of flash talks. I believe you get 2 minutes each. I'm just basically going to set a timer, and if it goes off, it means you're out of time, and if not, you're good. And I'll start when like everything is set up. So, yeah. You can.
Okay. Hi everyone, I am Romain Maccary, working at University of Vera. I'm working on prompt emission, and especially I'm trying to find ways to identify a GRB progenitor from their prompt emission properties. So GRBs have been traditionally classified into two classes, long GRBs being associated with massive star core collapse, while short GRB have been associated with compact object mergers. But we know that there are many exceptions to this rule, such as long GRB associated with mergers. And so we need to find other properties than the duration to better reliably classify burst. So in this respect, we found a very peculiar and distinctive properties in the Lie curve of long GRB associated with merger, GRB 230307A. In particular, the Lie curve of this burst is showing at the beginning of the event very bright, narrow, and tightly packed up pulses that are getting, as time goes by, progressively broader, softer, and more separated pulses. And this kind of properties is only observed so far in long GRB-associated mergers, and not in traditional long GRB associated with massive star core collapse. So we extended this analysis to a sample of GRBs detected by Fermi GBM, and we found 9 other candidates that are showing a similar evolution as in 230307A. And then we looked at their properties both in the Amati plane and in the T90 minimum variability timescale plane. And we found that their properties are more typical of GRB associated with merger than collapses. So if you want to know more about it, please come to see my poster. Thank you.
Hi everyone, my name is Jianghui and I work at the University of Bath. So my main work is working on modeling the afterglow of gamma ray bursts using the package Afterglow Pi. And in this study, I am actually using the BAT6 sample from Swift to find the population level physical properties of long GRBs. Because the BAT6 sample has measurements for most like the redshifts and fluxes in X-ray, radio, and R-band, I was able to find the population level physics of long GRBs. And I have some preliminary results shown here. The afterglow emission is modeled using Afterglow Pi, which has different viewing angles and jet structure. So after finding these properties of long GRBs, I was able to recover the distribution of fluxes of afterglows that are similar to the BAT6 sample. We can use these population level properties to do a lot of things. For example, we can predict the TeV afterglows. I have put an example spectrum, an example light curve here. And this is generated using the posteriors that we found from the BAT6 population. And right now we have some preliminary Thomson upscattering features in the Afterglow Pi package. However, to fully explain the very high energy emission in the future, for example, if we have detections from TAO, then we will need to include Klein-Nishina effects in Afterglow Pi, which is the next step in this study. I believe I have the poster outside if it's been put up. So if you want to talk more about this project, you can come to me or see my poster. Thank you.
Hi, Romain. My name is Berk. I'm a third-year PhD student at the University of Bath, and I'm currently working on investigating the effect of spatial resolution on the parameters we measure around transient environments. So it's quite common to look at the environments where transient has occurred in like star-forming regions to try and understand more about the underlying star population or the progenitors of the transients. And at local universe, because we have high resolution observations, it's quite accurate. We often get accurate results, but at high redshift, you might get contamination effects from neighboring star-forming regions or other non-star-forming regions, and which may affect our final results. So that's the kind of the effect that we're trying to investigate here. So we do this by looking at a sample of MAT galaxies that were observed by MUSE. We identify the star-forming regions in each galaxy and look at their chemical properties. Then we deliberately worsen the resolution to mimic an observation at a slightly higher redshift, and then repeat our measurements at these star-forming regions. And then we bin all the star-forming regions from all the galaxies based on their radial offsets from the galactic centers. And this allows us to make a plot like this, where we can plot the deviation of a parameter we're looking at with respect to the global properties as a function of spatial resolution. So there's a couple of things that we can take away from this plot. The obvious thing is that after a certain resolution scale, we start to sample the global properties rather than individual environmental properties. And we see some kind of deviation between the highest and the lowest resolution. And we also see the effect from metallicity gradients because of this kind of color gradient that's affecting some of the metallicities. So I have in the poster outside, and I have a similar plot for H alpha equivalent width as well. And so if you have any questions regarding this, I'm happy to talk more. Thank you.
Hello, my name's Anne. I'm a postdoc at the University of Bath. It's a big family reunion this session. I'm presenting the first time we've measured the very big red circle emission line in the spectrum of a GRB host galaxy. So we often use GRBs to find really dim galaxies, and then we use the imprint that the galaxy leaves on the GRB afterglow as a probe for the metallicity. And in this case, it is the oxygen metallicity, not the iron one. Don't be mad at me, Martyna, I'm sorry. It's the oxygen metallicity to add those galaxies onto like things like mass metallicity relations, where all the other galaxies have their emission measured or their metallicity measured from emission lines. And one of the big questions is whether or not we can actually do that, whether those two metallicities are the same. And usually emission line metallicities are measured using strongline diagnostics, which are relations that are calibrated on big samples of galaxies between ratios of different emission lines and the oxygen abundance. The question is, can we use those for gamma burst host galaxies? And that's a completely other different questions. So in this case, we can use the oxygen auroral line, which is the first time we've measured that one in a GRB host galaxy, to calculate the electron temperature-based metallicity, which are the two measurements on the left, depending a little bit on the relationship you use between oxygen 2 and oxygen 3 temperatures. And then the absorption-based metallicity from the GRB afterglow is the gray band. And you can actually see that they're sort of consistent for this galaxy, while the strongline diagnostics, depending on which one you take, as some of them are double branch, so you have two solutions, they actually don't really agree with the absorption-based metallicity, which is what we generally see for most galaxies for which we have both of these measurements. So at least for this one, it seems like it's okay to use the absorption-based metallicity to add stars onto emission line samples. But the sample size is 1. So if anyone's on the tag for JWST, please accept my proposal this time around. Thank you.
Hi, I'm Isabelle, or Izzy. My post is about extended emission GRBs. So I work on GRBs from compact object mergers, and traditionally these GRBs are short with durations up to 2 seconds, and they have a central engine powered by an accretion torus that forms during the merger, and then that accretion happens on timescales of order seconds, which matches short GRBs. But now we have some observations of longer lasting extended emission bursts of more like tens of seconds, and these are associated to compact object mergers through coincident kilonovae detections. But the short central engine shouldn't be able to produce these longer emission bursts. So what we're showing here is our thin shell analytical model that is able to reproduce the timescales of these extended emission bursts without having to increase the accretion timescale or add any additional energy injection parameters. So we launch all our shells within a 2-second window, which matches the central engine time. And then we launch them with an exponential launch profile in mass and Lorentz factor. And then we model the high latitude emission of the different shells, which is emission from wider angles that takes different paths to the observer. And we also invoke an expansion of the jet from a narrow chord Gaussian jet to a wider, more top hat-like jet. And using these features, we are able to extend the emission timescale to match that of the observed data. So that's what you can see in the plot here, where the different colored lines are 3 different example extended emission bursts, and the black line is our model overlaid on the top. And you can see that it also kind of matches the broad morphology of extended emission bursts with an initial peak and then more plateaued emission later. And if you want to know more, then come and have a chat with me and come and look at the poster. Thank you.
Hi, I hope I'm audible there. The thing is that I'm also a Bath person and only the unfortunate one who couldn't be present there because of the visa shenanigans. But here I'm presenting the work on stochastic acceleration in GRB afterglow. The thing is that usually usually afterglow modeling is done using your upstream to be either isotropic and homogeneous or wind-like. But because of the ubiquity of turbulence in astrophysical plasma, sometimes it becomes imperative to include the impact of turbulence in the afterglow modeling. And so we have presented here what will happen if you include turbulence acceleration as a reacceleration mechanism for the particles which have already been accelerated in shock acceleration. And here in the top left, I hope it is not left, it's a top right plot, you would see how the particle spectrum is changing along with how turbulence spectrum is changing because it is kind of feeding the energy. In the bottom one, you can see how the particle acceleration is happening with self-similar coordinate along with the particle cooling, so that we can get some sort of an estimate of how the timing is happening or how the interplay would play a role. And in the left plot, you can see some sort of a ACD that we have plotted over here and the light curve, where we can see that because of the stochastic acceleration and because of the turbulence injection, we can see some sort of a localized flux enhancement in frequency and also in the light curve. Unfortunately, I'm not the one who can say that my poster is outside. The thing is that my poster is I couldn't see my poster online as well because I was too late to upload that. I hope the LOC or the SOC would able to kind of communicate on that thing. But that's it. Thank you.